Lesson: Data collection and pre-processing for AI-driven risk analysis. Data collection and pre-processing represent the foundational pillars for AI-driven risk analysis in supply chains. The efficacy of AI models hinges on the quality and relevance of the data fed into them, and pre-processing ensures that this data is structured and clean, minimizing inaccuracies in risk predictions. Implementing robust data collection and pre-processing strategies allows supply chain analysts to leverage AI effectively, identifying potential risks and mitigating them before they materialize into significant disruptions. The first step in data collection for AI-driven risk analysis involves identifying and acquiring relevant data sources. These sources can be both internal, such as enterprise resource planning systems, and external, like social media, news outlets, and market reports. Each source provides unique insights. For instance, ERP systems offer transaction data, while social media can provide sentiment analysis related to suppliers and logistics partners. A practical tool for data collection is web scraping, which allows analysts to extract real-time data from websites efficiently. Tools such as Beautiful Soup and Scrappy in Python enable automated data extraction from the web, which can then be processed and analyzed for risk indicators. Once data is collected, the next challenge is dealing with data variety and volume. Supply chains generate large amounts of structured and unstructured data, and handling this data efficiently is crucial. Apache Hadoop and Spark are invaluable frameworks for managing and processing big data. These frameworks facilitate distributed storage and parallel processing, making it feasible to manage and analyze massive datasets. For instance, a supply chain analyst might use Spark to process sensor data from IoT devices across a logistics network to predict potential equipment failures, thereby reducing downtime and associated risks. Data pre-processing is critical to transforming raw data into a format suitable for AI models. This process involves several steps, including data cleaning, integration, transformation, and reduction. Data cleaning is the first step, which involves handling missing values, outliers, and noisy data. Techniques like imputation can be used to replace missing values, while statistical methods can identify and mitigate the impact of outliers. For example, a supply chain analyst could use the Z-score method to detect outliers in delivery time data, ensuring that the model is not skewed by extreme values. Data integration is the next step, where data from different sources is combined into a unified dataset. This can be challenging due to inconsistencies in data formats and naming conventions. Schema matching tools and ontology-based integration can help align data from disparate sources. For instance, integrating data from a supplier's database and an internal ERP system might require reconciling different naming conventions for the same product. Ontology-based integration tools can help standardize these differences, ensuring seamless data integration. Data transformation involves converting data into a suitable format for analysis. Normalization and standardization are common techniques used to scale numerical data, ensuring that it falls within a specific range. This is crucial for algorithms that depend on distance calculation, such as k-means clustering, which might be used to cluster suppliers based on risk factors. By normalizing the data, analysts can ensure that no single feature disproportionately influences the analysis. Data reduction is the final step in pre-processing, where the goal is to simplify the dataset without losing significant information. Techniques such as principal component analysis and feature selection are employed to reduce dimensionality. PCA can be particularly useful in condensing large datasets into principal components that capture the most variance, facilitating a more efficient model training process. For instance, when analyzing risks related to supplier performance, PCA might identify key factors such as delivery consistency and quality control that account for most of the variations in supplier risk profiles. Real-world applications of these techniques are evident in companies that have successfully implemented AI-driven risk analysis. For example, IBM's Watson has been used for supply chain risk management, leveraging AI to analyze data from various sources and predict potential disruptions. By employing advanced data collection and pre-processing techniques, IBM Watson can generate actionable insights, allowing companies to anticipate and mitigate risks proactively. Statistics also support the importance of data preprocessing in AI-driven risk analysis. A study by Kaggle found that data cleaning and organizing consumed over 60% of a data scientist's time, highlighting its significance in the data analysis process. Furthermore, research has shown that poor data quality can lead to a 20% increase in operational costs, emphasizing the financial impact of effective data preprocessing. In conclusion, data collection and preprocessing are indispensable for AI-driven risk analysis in supply chains. By employing practical tools and frameworks such as web scraping, Hadoop, and Spark for data management, and using preprocessing techniques like data cleaning, integration, transformation, and reduction, supply chain analysts can enhance the accuracy and reliability of their risk predictions. The integration of these strategies not only addresses real-world challenges, but also empowers professionals to harness AI effectively, ensuring resilient and agile supply chains capable of withstanding uncertainties and disruptions.